we don't have the whole function. We're missing this k value. So we want to find what k would have to be in order for this line to be tangent to this function. So visually, just to wrap our heads around what's going on, we have some x squared parent graph that's been vertically stretched or compressed, maybe flipped, we don't know. We do know that this tangent line is approximately like this. So we want to find what k would need to be in order for that line to be tangent to our graph, yes? Thoughts? Jaylen? So if you find your derivative of the function, which is going to use the power rule, you're going to bring your 2 out in front, yes? So it would be 2kx, yes? You want that slope, 2kx, to equal the slope of your tangent line, which is -2. And if you solve that for k, how are you? We want our slope, which is this, to equal -2. Why -2x? We want our slope to equal -2. So I don't think we have enough yet. Right? I think that there's another dimension to this that we're missing. Adam, what are you thinking? Well, the graph of the derivative would be a horizontal line. We think k should be -1. So that would just be -x squared, which is just this right here. And we want it to be tangent, so it would be tangent to it over here somewhere. Who's got another thought? Because I think there should be a system of equations here. Because on top of, because right now we have 2 unknown variables. Our derivative is definitely 2kx. And our derivative and our slope, definitely we want to know that it equals -2. But we've got 2 unknown variables here. Stephanie? Because our derivative formula is 2kx, just by the power rule. The derivative is not 2k. The derivative is dependent on the x location. So we have 2 unknown variables. What other equation could we write that would also have 2 unknown variables? The tangent line and the function have to share at least one point, right? So we essentially want to see where they're going to intersect, because that's going to be your point of tangency. So if this equals this, -2x plus 3 has to equal kx squared, there's a system for us. So we can address the 2 unknown variables part. I think this would be, if I divide both sides by 2 here, kx equals -1. And then it's probably going to be easiest to solve for k, yes? So divide both sides by x. So k is going to be the equivalent of -1 over x, and then we can use that back in here. Negative 2x plus 3. Equals, I replaced my k with negative 1 over x. And x squared. Now if I solve for x, that x is going to cancel one of those, equals negative x. Add 2x to both sides. So x equals 3. Yes? So if x equals 3, go back up here, that's telling us that the tangent location is going to be at 3 comma something. But go back up here, 2k times 3 has to equal negative 2. So that's 6k equals negative 2, and k equals negative 1/3 is the answer. So you guys all seem very convinced that k should just be, what did you say, negative 1? Right? Find k such that the given, so let's see visually why that wouldn't work. If k was negative 1, you'd just have negative x squared, and then you've got this negative 2x plus 3. It's totally missing it. You follow? If you guys just had stopped there and ignored the fact that there's an x coordinate involved with your derivative, and you just left that x off and set 2k equals negative 2 and thought k equals negative 1, you can see that that line is not tangent to that graph. So given that when we found our derivative there were 2 unknowns involved, we can't jump right to an answer. We have to find another equation with 2 unknowns involved. And the fact of the matter is the tangent line and the function graph have to share a point. They can't not share a point. They share the point of tangency. They share one and only one point. So if you set them equal to each other like we did, that gave us a second equation with 2 variables, and then we did a system of equations. So now we know that k should have been negative 1/3 x squared. And now we should see that our parabola got a little bit wider than you guys had it, just making it a negative 1. And that allowed the line to hit it and be a tangent, specifically at the point 3 comma something, right? 3 comma negative 6, but 3 negative 3 is the point where they're intersecting, if it ever asked you for the point of tangency. Okay? Questions on that? No. Okay. So let's try this one then. So find k such that the given line here is tangent to this one. So we need this slope to equal 1. So if we rewrite our function so that the power rule is, that's still my original function, just written a different way. My derivative is going to be equal to 1/2 k x to the negative 1/2, which is k over 2 root x. Make sure we understand that jump. The k is still in the numerator, the 2 is on the denominator, and the root x gets moved to the denominator. We want that derivative to equal 1. Again, way too early to know what k is going to be. We have 2 unknown variables that need to work together to make that happen. So our second equation is going to come from the fact that your tangent line and your function have to intersect at the point of tangency. So you'd set one function equal to the other. So k root x equals x plus 4. And then what's our best way of solving this system? What should we solve for and where? What's going to be the easiest to solve for and where so that we can do a substitution? This k, right? Well, I guess you could divide both sides by root x there, but then k would equal a fraction. You'd have a complex fraction once you plugged it in. So solving for this k, is probably going to be the easiest. Multiply both sides by 2 root x. So k equals 2 root x. Okay, go ahead on your own and plug that in. We have 2 root x times root x equals x plus 4. So 2 root x times root x is just 2x equals x plus 4. Subtract x from both sides. X equals 4. Once you know that x equals 4, we can go back and find k. So 2 root 4, 2 times 2 is 4. So k equals 4. You ready for my proof? Or checking our work with the calculator? So our function is supposedly 4 root x, and our tangent line is x plus 4. Moment of truth. It's very sweet. Window. I'm going to go 0 to 10 and 0 to 20. Then it should be clear. Are you satisfied? You look like you have a question. Yeah. So once I knew one of the variables, just like I said, I just went back and plugged it in. So k was supposed to equal 2 times whatever root x was going to be. So if x is 4, root 4 is 2, and 2 times 2 is 4. What did you get for k? Where did you go to find that? What did you do with your x equals 4 to find that? Well, no, I got x equals 3, and so I went back to my k equals formula, and just now that I knew that x was 3, I just plugged it in so I could see that k equaled negative 1/3. Oh, so in this one I went back to this equation. So you went back to your derivative equation right here. So you did this one. Really. You really plugged it back into this one. So same thing. You can do it this one too, but same thing. If x is 4, the square root of 4 is 2. 2 times 2 is 4. So k over 4 needs to equal 1. So k has to be 4 there too. So it's, you could plug it into either spot. I don't know why I did it differently in each case. You're right, it would have been, I should have just gone back to my k equals 1 over here like I did over here, but for whatever reason I went back into an original. Anything else? Okay. In B, we have a g of x equation that is 3 times the f of x equation minus 1. So what is the relationship between the derivative of f and the derivative of g? So we have a random function. Once we stretch it vertically by 3 and then shift it down 1, what's the relationship between the derivative of each of those? Let's discuss. What are your initial thoughts? How about for bonus points? Put some on. Go ahead, Jane. Go to the board. Oh. Okay. The down one doesn't matter. So what would the derivative of one of these be relative to the other? What would the relationship be? No, you're not. I don't think you're wrong. I think you're right. I think you are not explaining it well. Josh? There is a 3-to-1 ratio, but I think you said it backwards. This is going to be 3 times whatever that is. Okay. We got it, or they have it. They understand it, whether they can write in a sentence or not. What is the relationship between f prime of x and g prime of x? G prime of x is going to be 3 times whatever that is. Right? The slope of g is going to be 3 times the slope of f. Because no matter what f is, we can just do a random, pretend that's f of x. If we create g of x, we're stretching it vertically by a factor of 3. So that's going to go up 3 times as high. That's going to go down 3 times as low, and so on. So that would be our g of x. 3 times as steep. Then when you shift it up 1, as Jalen said, the shifting up 1 or down isn't going to affect the slope at any location. Whether, when you slide things up and down, we don't affect it. So g prime of x is 3 times f prime of x. 3 times f prime of x. You could literally like g prime of x equals 3 times f prime of x. Any questions on that? Okay. Show that y equals x and y equals 1 over x have tangent lines that are perpendicular to each other at their points of intersection. Ooh, this is fun. First of all, let's do a sketch. Y equals x. And then y equals 1 over x is just your parent graph for a rational function. So they want us to show that at their points of intersection, so let's say this one for starters, that their tangent lines are perpendicular to each other. So the tangent line of the 1 over x looks like this, ish, right? And what does the tangent line of the line look like? It is the line, correct. So you can kind of visually see that their respective tangent lines are perpendicular to each other. It wants us to show it, let's just assume algebraically. So let's focus on just this one first, and then the other one would follow suit. What would you have to do first? Find the point of intersection, so set them equal to each other. So x equals 1 over x. Multiply both sides by x, you're going to get x squared equals 1. Okay, well this is actually going to give us both points of intersection because x equals plus or minus 1. So one of the points of intersection is at 1 something, and the other point of intersection is at negative 1 something. This one particular, when we plug in 1, is obviously at 1, 1. So then, if we know, let's just focus on this point of intersection first. At that point of intersection, we want to find the derivative of one graph versus the derivative of the other graph. Yes? So it's kind of unfortunate that they're both y equals. So this one, y equals x, has a slope of what at 1, 1? Right? And that's just because it's a line, so y prime in this case is always equal to 1. the y equals 1 over x, we want to find that y prime first. So I'm going to rewrite that as x to the negative first. So y prime is going to be negative 1 x to the negative second. In other words, negative 1 over x squared. So this function has a slope of what at 1, 1? Right? When you plug in 1, you're going to get negative 1. And a slope of 1 and a slope of negative 1 are opposite reciprocals. Opposite reciprocals means perpendicular lines. And then the same thing would happen over here. Without showing it, obviously we have a tangent line there for the curve, a tangent line there for the line. They're perpendicular to each other. Any questions on that? Okay. Finding the average rate of change, which we've been doing in since algebra 2. This one's on a trig function. So to find the average rate of change, that's just a slope. So we need to find the 2 points. 0, comma what? 0, 0 for the sine of x. And pi over 6, comma what? 1/2. So my average rate of change is going to be 1/2 minus 0, which is 1/2, over pi over 6 minus 0. So if I keep, change, flip, because that's just a fraction divided by a fraction, keep, change, flip, that's going to be 3 over pi. The average rate of change is 3 over pi. How does this compare to the instantaneous rate of change at the endpoints? So to find the instantaneous rate of change, that's the derivative. So we want the derivative at each of the 2 endpoints. So let's first find our derivative formula. What's f prime of x? Cosine. So if we find the derivative at the 0 endpoint, the cosine of 0 is 1. And if we find the derivative at the other endpoint, pi over 6, cosine of pi over 6 is root 3 over 2. So when you're asked to compare, how does this, the average rate of change, compare to the instantaneous rate of change at one endpoint versus the other? What are they getting at here? Let's see. So if I sketch the sine of x curve, they're looking for the average rate of change from 0 to pi over 6, which is really there. Agreed? They're asking me to compare this average rate of change, which is not really supposed to be totally on top of the function, but it's too close to call. This average rate of change, how does that compare to the slope at 0, which is 1, and the slope here, which is root 3 over 2? What do you think? Right, it's just in between them, I think, is what they're getting at. So if I really accentuate what's happening from like here to here, there's your average rate of change. Your change instantly here is a little bit steeper, and your average rate of change here is a little bit less. So this is going to be somewhere in between them. Right, 3 over pi, 3 divided by 3.14 is 0.95. So it's a little bit obviously less than 1, but greater than root 3 over 2, which is 0.866. 0.866. So it is in between. Just kind of exploring type stuff. All right, the last one. If a ball is dropped from a height of 100 feet, here's my graph. its position height function after t seconds is given by that equation. Find the average velocity over each interval. Use the calculator. So your average velocity is essentially your average rate of change. So from 1, which is the point 1 comma 84, and then at 2 seconds it's got a height of 36, right? Wait, 2 squared is 4. 4 times negative 16 is negative 64 plus 100. 36. So your average rate of change here is 84 minus 36 over 1 minus 2. (48) over negative 1. So negative 48. How's my mental math there? Did I do that right? I need you to audit me. I could have gone either way. If I did it your way, I would just have a negative 48 over a positive 1. So they'll both end up being the same. As long as you're consistent. I started with this point on my y's, so I have to start with the 1 on my x's. So negative 48 between 1 and 2. So 2 is like here. Before we actually calculate it, if I'm doing between 1 and 1.5, what happens to this average rate of change comparatively? Is it as strong or no? No, right? It's still decreasing, but obviously not as steeply. That's not a word. In not as steep of a way. So 184 and then 1.5. We should just get still a negative slope, but not as much of a magnitude. Negative 16 times 1.5 squared plus 100 is 64. So that slope formula is going to be 84 minus 64 over 1 minus 1.5, which is going to be 20 over negative 0.5, which is going to be negative 40, like we thought. Still negative, not as steep. And between 1 and 1.1, still negative, but not as steep. So 1 and 84. And then 1.1, I'll do it with my calculator, negative 16 times 1.1 squared minus or plus 100 gives us 80.64. So your slope is 84 minus, what are we, this progression that we're going on, what are we technically getting closer and closer to? Right, the slope specifically at 1. We're kind of pinching a second value closer and closer to 1 to see what the secant line's slope is getting closer to. What is it, 0.64 divided by negative 0.1? We give a negative 33.6 slope there. So again, still negative, not as strong. So this formula is just kind of highlighting the fact that the derivative of your position function, the rate at which your position is changing, is your velocity. Okay? Which, have we done this before or no? In here. It's really a physics thing. Who's taken physics or is in physics? Have you done this? Do you guys do derivatives in physics? Conceptually, yeah. So if you know the position function now in physics, and you want to find the velocity of the object at a certain point in time, you just derive your position formula. So we'll see an application right here. They give us the position formula, and really at the end of this they want, what is the diver's velocity when he hits the water? So first of all, when is he going to hit the water is when your position function is going to equal 0, and that's just solving a quadratic. So negative 16t squared plus 16t plus 32 equaling 0. If I divide everything by negative 16, that's going to be a fairly easy thing to factor. T minus 2, t plus 1. It's going to be at 2 seconds. So what is your velocity at that moment? So since your velocity formula is always just going to be the derivative of your position formula, what is the derivative here? Negative 32t plus 16. So if this formula, which is, again, I'll put in parentheses, that's s prime of t, is going to give us our velocity at any time. So right when we hit the water, negative 64 plus 16, negative 48, oh, we don't have units, meters per second, we'll say, sure. Meters per second. Does that mean anything to you? No, I know, but like, no, I know. But like, if we were talking to the average person, is that fast? Is that not fast? Really? And it's hard to say because they didn't, I'm sure I stole this from the book, so we'll see. But like miles per hour does better for most people, right? How would you feel about converting that to miles per hour? Well, I mean, no, I don't need to talk about that. What section am I in? I'm sure I stole this from something. Driver's height. And I'm sure I paraphrased, which is why I'm missing. Oh, I'm in the wrong section. Hold on. A coin drops, a ball is thrown, a projectile is shot upward. Oh, got it. Feet. And seconds. So this is technically feet per second. Is that high? Do you know what that is? Okay, let's translate this to something that's going to be meaningful to people. Negative 48 feet per 1 second. Do you remember how to convert? Times. We want to get it out of feet and into what? Miles, right? So feet goes in the bottom. You put 1 mile up top, and how many feet are in a mile? 5,280, right? This is us multiplying by 1 so that we're not going to change the value, but our units are going to cancel and it's going to turn things into miles, yes? And we don't want it per second, we want it per hour because that makes sense to us. So we want our seconds to cancel, so we put our seconds up top. And we want to change it into an hour. So how many seconds are in 1 hour? Okay, so multiply those numbers across the top. Where's my calculator? 3,600 times 48 is 172800 and 5280. Do that division and you get 32.72 repeating, and your feet canceled, your seconds canceled, and you were just left with miles over per hour. So that's miles per hour. Remember doing that? Algebra 1? Physics. So raise your hand if you're not in physics and haven't taken physics. Oh, it does? So does that look more foreign to you guys? Okay. So you'd hit the water at 32 miles per hour. I don't know if it seems pretty fast to be flying through the air. Anywho, Homework starts bottom. Have a great weekend.